If you may turn on your video, it will be great to see you.
Believe me, not in this shape. It's not great.
Okay, so we'll talk about data visualization techniques and types of charts which we may use in data analysis projects. You know that when we are working with the numeric variables, it's really impossible to analyze some tendencies in the data set. So data visualization allows us to represent data sets and make some conclusion about these data. And data visualization is a form of communication that portrays dense and complex information in a graphical form. And the resulting visuals are designed to make it easy to compare data and use it to tell some story, both of which can help users in decision making. For us, our users are doctors, so we prepare some data in order to make the decision making process easier. And data visualization can express data of varying types and sizes from a few data points to large multivariate data sets. And also it's some problem how to represent data set if you have millions of observations. It's one side of visualization, and if you have a few data set, it's also sometimes a problem how to visualize all these 10 points, yes, and tell some story using the data. Data visualization should be accurate, helpful, and scalable. You may find this presentation in our classroom and follow links which you find inside the presentation to the full article about data visualization techniques. And so you should present your data in such a way that doesn't distort your information. So it should be clear representation without some additional non-useful information. So only you should visualize your data and don't distort your view. It should be helpful. You have some aim of visualization, so help users navigate data with context and affordances that emphasize exploration and comparison. And scalable, of course. Adapt visualizations for different device sizes. When we are talking about mobile phones and desktop application, you know that nowadays website has actually several variants of web page, yes, for mobile phones and for desktop. Actually, when you are preparing your application for patient monitoring, you need to adapt this application for different devices. And also, when you collect a lot of data, it should be the same as you have your data size. And if you visualize your accumulate, for example, data during patient monitoring, you need to visualize it in such a way that you may monitor 1 day, 10 days, or I don't know, 1 month, and you need to represent your data sets in all variants of duration. Let's look to types of charts which we may use when we are trying to visualize our data set. There are a lot of hundreds of variants how to represent your data set, but we will look in some popular, most popular examples. And you may see somewhere bold font. Bold font means that we use these charts in medical applications and biomedical researchers. So when we want to represent changes over time, we may use lines, we may use bars, yes, stacked bar charts, candlestick, area charts, timelines, horizon charts, and waterfall charts. I think that some of these types are really, you know these types. Ordinary line, the most popular chart in the world. I think. What do we have here on X and Y axis? I will take my pen and I will add some comments to the plot. One moment. So also helps me to so what do we have here as the X? It can be time, yes. It can be counts. For example, 1, 2, 3. It can be with units, with same steps, so some periodic observations. For example, our signals, yes, ECG signal, all biomedical signals actually, biomedical signals. And here we have some amplitude. For example, yes, it should be measured in microvolts or millivolts if you are talking about biomedical electrical signals. But also it can be how many, I don't know, how many steps you've done today. Yes, so it doesn't matter. But we want to show the trends of our data D, yes. When we are talking about bars, we have some parameter, but actually, yes, sometimes bars are really popular in visualization. For example, again, steps number during the day, yes, so it will be day, for example. I don't know, 1st of October, 2nd day, 3rd day, 4th, and so on. And here I have some scale actually for your amount of steps per day. It can be also number of arrhythmic contraction of the heart during the day. Stacked bar, when you combine several groups in one plot, you may also, I don't know, cooperate several events. Could you say some example of stacked bar? Actually, here we have also time because we are talking about changes over time. We may also have days here, for example, and here we may have activity, yes. Here will be ordinary walking, for example, and here we may have, for example, running, yes. Also represents how comparison between two groups, activity type of running and activity type of working. Yes, and changing over days. Interesting chart candlestick. Have you ever heard about candlestick charts? Could you just write to the chart plus or minus? Do you know what is candlestick? Harold, Dimitrios? Anyone else? Plus, minus? Okay, so we just, I want you to show this interesting example of chart. It's a little bit specific because actually it's not popular in medical data analysis, but it's really popular in stock markets. Yeah. So candlestick show some specific properties in trading. Yes. When you have price for the open, when you open your day and close the day with some price, you have the highest value of your price and the lowest one, and you plot these candlesticks, one candlestick for one day usually, or something like this, and you may analyze the dynamic of the price. Yes, and when you use red color, it means that you close the day with price lower than price were when the day opened. So, and the green one will be when price will be higher at the end of the day. So you may represent dynamic of the price and trading. But it's like an example. Yes, in medical applications, I did not see these charts actually, but you may use it. Why not? For example, for heart, not heart rate. I don't know. Maybe heart rate. You start with when you wake up. You may measure your heart rate or saturation level and analyze this level during the day, or temperature, for example, of the patient. And represent these data in compact form. Yes, so it's like a compact representing of the several observations for one day, for example. Area charts and horizon charts, they are quite close to each other. We just fill the area between the line using some color. It also allows us to represent some trends. If we are using line, sometimes it's really when you want to represent only one line in one plot, it can be not pretty look. So we may just fill the area under the curve, and it gives us more feeling about some integral representation of the data. Timeline. In timeline, we also, as everybody here, have some time scale, and we may add some events. For example, wake up. So, for example, it will be breakfast, lunch. Yes, I know. Dinner, something like this. Yes, you have points that correspond to some events, and add some comments to these points. It also allows you to represent some time scale. Horizon, you may use it to represent several synchronic lines, and you may also stack one area under the other. So I will show you example in some video. You will see how to use horizon charts in order to represent the data. It's also close to bar. you see, because you may just add some line here and you will obtain actually the same result. It will be close to horizon. It's also in when you have some aim to compare two groups. And waterfalls. Waterfall is also interesting type of the chart when you divide your time into some regions, and you also have minimum value and maximum value of some data, so range of the data per day. For example, heart rate again, yes, you have minimum value, maximum value, and you collect all data inside the day and plot this rectangle to the plot for 1 day. The second day, you will have some new values, and you also add it to your waterfall chart, and so on. So, for example, here we'll have days, heart rate, for example. Yes, and here will be minimum value and maximum. Something like this. It will be waterfall chart. It's also not very popular in biomedical applications, but you may use it in your projects. Why not? If you want to compare some categories, you may use these 6 types of charts. Again, bar, but here you have not time as axis, but here you have, for example, groups or also days. Let's take groups, yes. For example, you may divide your patients through some ages. Yes, let's do it age group. The first group will be children, yes, before 10, yes. Here we will have from 10 to, it will be teenagers, yes. The second group will be adults and people older than 25, for example. Yes, and you want to compare, I don't know, activity level, yes. You may plot these bars. It's also will be really representable. You may see the differences in inside your groups. But sometimes you have, for example, not activity level, but level of the pain. For example, pain level. For patients, again, let's save this example with ages, age groups. And it will be drug number, drug A, and drug B. And we want to compare how drug B and A influence to the pain level, yes, for several groups of patients. And for example, here we see that drug B, the patients from the group number 1, it will be our child's before 10 years, that drug A will be better for them because the pain level will be less than for the drug B. But for older patients, drug A, patients with it's drug A, they feel pain with the higher level than patients from the B group. So you may also analyze differences patients. Bubbles. It's really funny way to represent your data set, and I will show you an example. Oh, not here. Oh, where is it? Where is an example with bubbles? I will stop my demonstration, and I will show you example with bubbles. One moment. This is a great example of data of funny data representation, and I hope that you will that I will share my voice, the music from the video. One moment. Demonstration. Could you write to the chat? Do you have? Do you hear text from the video?
Sorry, right? What?
Pardon?
What do you want us to write?
Everything okay. I just want to be sure that you have you hear a speaker from the video in our translation. Yes, I know that it can be not accurate the same that you are watching video, but just I want you to show 4 minutes of data visualization, and please hear the speaker from this video. I will also send this link to the chat, so you may, if you don't hear or don't see well, you may start this watching this video by your own in your computer, and I will do it here.
Video don't have sound.
So I think that is really a good example of how data visualization can represent the tendency in data. And you see that he used bubbles in order to demonstrate size of the country, yes, and color of this bubble reflect the part of the world, yes, to which this country belongs to. And really, really interesting. You may also find other videos from Hans Rosling in YouTube, and he has a full video for 1 hour about population. Also, I will send it to our chat. You may look this video also when you have free time, just to get you will see some visualization techniques, and you see that this video is also not from the last years. It's from, I don't know, November of 2013. So it's 7 years. Yeah, this video. Yes, the first video for 4 minutes from 2010, but the second video of 2013. Okay, we will continue talking about represent. So it's about some example about bubble charts. I really like bubble chart, but it's they're good for when you have some categories or you have comparable sizes of bubbles, because if you have if you have groups of observation, when you have small bubble and big bubbles, and it's really not very good to use when your sizes varies in high scale. So you may play with charts in order to find the best way to represent. Okay, parallel coordinates. It's also one of the most popular plots in comparison between groups, but it's not popular in medical statistics, so I will not talk about it anymore. Multi-lines. When you have several trends in data, you may plot several lines in one chart and compare the results. And a bullet chart. A few words about bullet chart or bullet graph. It's interesting approach to visualize your data when you have some quantitative scale from 2. You have your actual value. It's black one. Yes, the dark center line represents the actual value of your parameter, and the dark vertical line represents a target value. The colored bands represent ranges such as poor, average, and good. So you have 3 regions. And bullet graphs may be horizontal or vertical and may be stacked to allow comparison of several measures at once. You may use this representation in order to show the revenue of your hospital, for example, and something like this. So I think that is interesting approach because I haven't seen it before, and you may also use it. For example, you have to motivate your patients to increase activity level. Yes, it will be good motivation to move from the green or dark gray region with poor activity to the target value. Yes. And also some comments about bar chart and histogram. I want you to be sure that you understand differences between these 2 types. When we are talking about, they are quite, they're close to each other, but we have 2 main different two different ways to use bars and histogram. It's also rectangles. in the first case, in the second. But when we are talking about a bar chart, we mean that we have some categories as x-axis and numeric values on the y-axis. And we have gaps between our bars. And we just need to compare several categories or groups. We may also use bar chart when we want to show some variation during the time. So we may have not categories on the x-axis, but also time. But when we are talking about histogram, we have numeric ranges as x-axis and frequency count as y. So also we have no gap here, so our bars quite close one to another. And as for application, it's histograms using to, for example, to compare several groups. In this example, we have weight as numeric range, yes, for the x-axis, and count how many patients from this group, yes, in the range from in this range. So yes, don't forget that histogram represent density of how many observations we have in some range. Here we have some parameter and value counts of observations, number of observations in this range. You may see also these vertical lines here. It's also some type of chart, also one more chart, how to represent densities of your observation, but you see that you don't see difference between sometimes when you fill your space with these vertical lines, you couldn't separate density actually, because in one-dimensional, it will be one-dimensional plot, yes. You may use it, but also you need to understand limited of this chart. So histogram is one of the most popular data chart in our field. And the third application of charts is to represent correlation between several features. Scatter plot chart allows us to represent data in two-dimensional space, so it's 2D plot also. When you have two features, feature 1, feature 2, and you have observation, and you plot these observations using some marks, circles, I don't know, squares, and something like this. You may use, and you will see, do you have any correlation between F1 and F2? Because if you have plot like this, you don't have correlation actually. So this correlation is close to 0. And when you have plot like here, you will see that correlation is close to 1. Could you write to our Zoom chat? Do you know what is correlation coefficient? Could you just plus or minus? Are you familiar with this term? Mm-hmm. 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 Some of you is familiar, not. Mm-hmm. I will explain it on hands, but I strongly recommend you to read information about correlation coefficient. Correlation reflects linear dependencies between some features. In our example, we have two parameters. for example, I don't know. There are some questions. Okay. For example, we have income, age, and income. And we know that between age and income, we have some relationship, yes. And sometimes, using some mathematical equation, we may calculate correlation between age and income. And for example, we will see that correlation coefficient is equal to 0.7. Correlation coefficient varies between -1 and +1. And when it's close to 1, it means that we have positive correlation between F1 and F2 or some other features. So our age is strongly correlated with income. If we have correlation coefficient close to 0, it means that we have weak correlation between features. So when it's close to 1, it means that we have strong positive correlation. If it's close to 0, no correlation. It means that one feature does not influence to another, so they independent. If you have a correlation coefficient which close to -1, it means that we have strong negative correlation.
Can I ask?
Yes.
Why did you say on the first on the scatter plot that the correlation is close to 0? I mean, if you compare it to the one that you created, on the other, yeah. If you compare it to the one that you created right under, it looks like it's close to -1, isn't it?
Yes, we may try to construct here some line that represent
Yes,
dependency.
exactly.
Yes, tendency in data set, but actually we divide our data in 4 parts and calculate values in these four areas. Actually, yes, I approximately close to it closely to 0 than here, because we see that the variance of the F2 is not less correlated with variance of F1. So when we are talking about dependencies, we are talking about variance of data sets, actually. And we will talk today about covariance matrix, and this matrix consists of variances and correlation coefficients, actually. So correlation reflects linear dependency between two data sets. And actually, one note that we are talking about linear correlation. So when you have something like see this, so you have some sinusoid in the basic in basics. So here you have non-linear correlation. Non-linear. And if you calculate correlation coefficients, I don't know what do you have here, but there is no linear correlation here. So here, our correlation coefficient reflect actually some tendency in our data. Bubble charts may be also useful when we are talking about correlation, because as you've seen in our example, you may plot bubbles, but you use size of these bubbles and color in order to represent some groups. But actually, it's scatter plot but with marks with different sizes. Column and line charts. Also, you may use charts, bars and lines in order to reflect do you have the same tendency in some parameters? For example, again, level activity and, for example, level of the sugar in the blood. You may plot in one chart several parameters and analyze using visual analysis, analyze correlation between them. And heat map charts. In heat map, we may use color of the area of the squares in order to represent also density of our datasets. For example, heat map, actually, we have, it's a two-dimensional histogram, actually, because we have some numeric values, for example, also feature 1 and feature 2. And we have some color scale. For example, for the white squares, it means that here we have 0 patient with in this range of our features, yes. But here we have, for example, 10 patients with some, for example, here we have weight, here we have sugar level with some weight and some sugar level, yes. So we divide our numeric range into parts and calculate how many patients we have with the values of F1 from this to this and feature 2 from this value to this. I will show you an example, you will understand. We may have here numeric values. We may also plot it for several categories or groups. Correlation coefficient close to linear regression, actually, because do you remember that in linear regression we calculate R-square values? R-square value is actually square of the correlation coefficient. It's really, really close. They are about the same thing. But when you calculate correlation coefficient, you don't plot the regression line. It's like my visualization. It's only coefficient without any lines and something like this. So it's numerical. It's numerical evaluation of dependency of some trend in data. So it's about correlation, how to represent correlation between several between two features. When you want to describe some distribution of parameter, you may use also several charts. Histogram, you know what is this? You have some several ranges of your numeric value. You calculate how many points from each range and plot these bars. Box plots, it's really, really interesting way to represent your data if you have a lot of data. You calculate mean value, you calculate deviation of this value using variance and minimum and maximum value. And violin is also the same way to represent your data, but using this funny shape. And density plot, it's also like a histogram, but you have bars with a really small range. And you just plot it using a continuous line. About box plot, I don't have information here, sorry. You will work with box plots in your lab work, and you will find, I don't know why I didn't add information here. You have some median value here. So it's like, actually, if you have some histogram, I don't know, like this, yes. You may plot your box plot, it's also data representation, but in more compact form. Because, for example, you have 4 groups or categories. And if you want to plot its distribution of some parameter, for example, heart rate for 5 groups, and you divide your patients by age, and you want to compare some distribution of maximum heart rate in your data set, you may plot 4 groups in one plot. You see, but for histograms will be really hard to analyze. But when you plot your distribution, your density, your distribution of parameter using box plot, you may plot 4 groups. You see here, for example, yes, and you will see that for some of them, for example, for this, you have median value less than for another's. And it will be easier to compare more than 2 groups. If you have more than 2 groups, it's better to use box plots. In our presentation, you will find 4 links to articles about data visualization techniques. I will just show you some of them now. One moment. I strongly recommend you to go through these articles, maybe not it. So for example, this web page, yes, you see there are a lot of bars, charts, yes. For example, this radial column chart and explanation. What is this? When you need to think about data visualization, when you want to analyze, firstly, when you want to analyze what do you have inside your data set, you need to plot something for your own, because in the base of visual analysis, you make a conclusion of what you should do next, or which type of algorithm will be better for your data. So for better data understanding, bubble chart, yes, actually here. And I think that these visualization techniques so popular nowadays because we have computer technologies, and it's really easy to visualize this data on the screen, yes, because it's impossible to do using paper, yes. So here also some examples. And in this data.wiz.com, you may find gallery with examples of these plots, and you see that you may also find script how to plot this data. And also we have some tendency that all our applications goes to web, because it means that you don't need to install some desktop application. You don't need to buy some computer which will be suitable for some calculations. You might just go to website and do what you want in this website. So web visualization is really popular area. And also there are some interactive features when you may see some tooltip, yes, when you move your mouse and you see message here, yeah. So it's our heat map. And I will show you some examples. in application. And one point about dashboards. In a healthcare organization, you have a lot of data which you need to analyze to better performance of your hospital. Something like this dashboard enable healthcare organization to assess their overall status by providing them with key analytics and replacement they need to review several detailed reports. They can be utilized, track revenue cycle performance, help meet meaningful use standards, and monitor disparate processes for more efficiency. Furthermore, dashboards can integrate with electronic workflow management solutions and identify areas for operational, financial, and quality of care improvements. And dashboard consists of several parts with the main statistics. And it's really, really difficult to construct such a dashboard, which gives you a lot of information, but in some compact form. And you understand that when we are talking about patient monitoring system, it's also impossible for a doctor to go through all period of observation. For example, you monitor a patient during the week. You collect a lot of data, and how to represent these data to the doctor. It's a really good question because we don't know what should we give to the doctor for better diagnosis, or for we need to work with our with collected data. We need to find something interesting and to represent to the doctor and say, look, I think that we have some problems with sugar level. So look to the sugar level distribution during the days, and you will see that in the morning, sugar level is too high, I think, for my patient. So we need to add it to the dashboard. And for healthcare organization, you see here, for example, with COVID's operation dashboard patient flow, and it allows you to evaluate and monitor operations broken down by 3 primary stages in the hospitalization life cycle. So you see bed analysis, some management, patients, and bed days. Yes, actually bed days are very, very important for us. Yes, because we want to make this parameter less as possible. Yes, new patient, existing patients, dynamic. So here we have tables. Here we have some bars which reflect in some numeric range. We have lines. We have bars, vertical and horizontal. So there are several type of graphs. And some examples from my projects, which we did this year in my company. This example, we had some task to visualize dynamic of heart rate and arrhythmias for a patient. Here we have lines. It's trends of heart rate, as I remember, or maybe not. Heart rate, ST. I don't see legend here, unfortunately. So, oh no, it's max value of heart rate, mean value of heart rate, and mean and minimum value. Yes, so it's some range with the heart rate, and we divide our time into parts for half an hour. You see that we have step half an hour, and we here we have some sleep period from here to here, maybe. No. And here we have number of arrhythmia, and there are some 6 types of arrhythmia events. And also we may see distribution of ST segment, QT segment, PQ, and blood pressure level. So we may analyze distribution of these parameters for this period of time. You may see also these plots for index of apnea and hypopnea. If it's red, it means this index greater than 15, and we have a lot of apnea and hypopnea events in this period. Okay, and the second one, the second example is page from our program for Holter records analysis. This page where doctor analyzes PQ value. This is segment before the QRS complex. This wave you see in this in the left part of the screen, you see average P wave. It calculates from, I don't remember, from a 1 minute of observation. You just calculate some average example of P wave. In the second plot, you see some interval of the signal in 1, 2, 3, 4, 5, 6, 7, 8, 9, in 9 leads. And here you have trend of this P wave, and it also you see that we have 2 colors in order to represent the front of this wave. It's positive or negative. And also we have some trends for the 1 day, some events here, some also events here. It's sleeping time here. This rectangles reflect sleeping. Here we have scatter plot, but you see that it's actually a heat map. Yes, we may also analyze the distribution of the RR interval and PQ interval. We see correlation value 0.85 and a range of our values. And also we have histogram, and you see that we have some blue rectangle here. It means that in this position, our data, our PQ interval lies in this bar. So we see some cursor here. Yes, this position of cursor. So it's also some integral representation of your data, but it allows to the doctor analyze some complex view of event, because if you have if P wave is really important for some cases, for some diseases, it's also bad if it varies a lot. You have deprivation or increasing of this P wave. So you need, you give your doctor some instrument to analyze this property of the ECG signal. And some example with apnea, hypopnea events during the night. Here in this part of the screen, you see airflow from the nose, and here you have motion and RR interval, so distance between 2 complexes. And these rectangles reflect apnea and hypopnea events, and you also have these events. So here we have hypopnea with duration 44 seconds. And here we have also some events on our signal. We may also see these events here. So here we have some apneas and hypopneas in this screen. Also, we have synchronized ECG signal, and you also see this cursor. Yes, here and here we also have our cursor. And you may see that in this plot you have the whole day. So it starts from 2 p.m. and goes to, I know, 10 a.m. So you have night period somewhere here, because this is sleeping time again. And you have bars which represent level of the oxygen level here. So oxygen level is actually, you have some problems with it, because I think that there are a lot of, when you are using saturation level, when you analyze saturation using SpO2 device for your hand, it's you don't wear it during the day, and you have a lot of observations where oxygen level is weak. And also you have some table with statistic, how many apneas you have, hypopneas, and total value of these sleeping disorders. So also you see that there are a lot of information in one screen. Yes, trend, some here you'll see it's motion, here bars with motion. And we got you need to know how could you represent your data for better analysis. And the last example, I think that it's last example. Also, we want to analyze efficiency of antiarrhythmic therapy. And this efficiency analyzes when you have some observation before some drug and after the antiarrhythmic therapy. And you will see in this example that for the first fragment, it's when your patient without any drug in his normal state. And after the therapy, it will be the second group. And you see that arrhythmia, that in his usual state, this patient has a lot of arrhythmias of this R, C, and C type. And after the therapy, number of these arrhythmia events less than before the therapy. It's good. So you may see that we have also some conclusion here that number of some arrhythmia greater than before the therapy. So we have more grouped arrhythmias, but number of single events less in 5 times. And also we have some heart rate distribution for 2 fragments, and mean values will be here. So we see that mean value of heart rate less than after the therapy than before. And also some trends. And here you see that we select some region and plot this region, this trend in some other scale here, heart rate. And also arrhythmia, we see that in this period of time we had 11 arrhythmia events, and this is single arrhythmia. But here we have also distribution of our arithmetic. And you see that we have some problem actually here. When we are using color scale, we need to visualize if you have one arrhythmia, it's important for us. But the step between 0 and 1 really weak. So I decided to add also numeric values of this property. So we also using numbers in order to clarify this parameter. So some event, and this is web technology. You may open this HTML page in browser. Okay, do you have some questions about charts and visualization in general?
Not for me.
Nope, I don't think so.
We have 5 minutes break, okay? And after that, we continue talking about principal component analysis, and just it takes a lot of time to describe basic information about visualization, but I think that it's okay. We have 2 classes today, so we have this time. 5 minutes break, and we will continue.
Okay.
So let's continue. Okay, principal component analysis, PCA. Actually, it's one of the dimensional reduction methods. It's really popular because it's simple and gives some good results in some applications. But actually, dimensional reduction, it's not only PCA. When we may use these actually dimensional reduction methods. And we have, when we are talking about multidimensional feature space, we mean that we have observations, some patients, I don't know, website visitors, and something like this, customers. Anyway, we have a lot of parameters which describe our object of observation. Again, weight, sugar level, age, gender, and many others. And when we want to represent our data in some plots, in some free or d-dimensional chart, we could not do it in one page. So we could not analyze distribution of our parameters and how do they connect. In this example, we have 4 features of Fisher irises. You will work with Fisher irises in our lab works, and some of you know what is it. We have sepal length, sepal width, petal length, and petal width. And if you want to analyze how do they distribute one parameter from the other, we need to plot these 16 plots. Yes, so we may use histogram for one parameter to show distribution of one parameter, and scatter plot. And it's really bad to plot all of this stuff. For example, you have 20 parameters. How to represent your data in one chart? It's impossible. So we have some problems with visual analysis of our data set. And also the size of the original data set may be too big. And we have some problems with storage, with data storage, because when you collect data from thousands of patients, you have 1 gigabyte per patient. So if you may remove, I don't know, 80% of information of, if you may decrease the size of your file, yes, but save important information, it will be great because it allows you to use less space in your server or computer and collect more patients in one hard disk. And also we have problem with garbage information because it mixed with important features. So we have some problems with the future analysis. So when we have garbage information, it's better to remove it from the data set. It's like a filter for our data. So when we reduce the number of features, we may visualize our data and analyze it visually and make some conclusions about dependencies in data, distribution of the data. It's something like this, all this visual stuff. We may reduce the size of data set and save some space in our computer and server. It's also important when we collect a lot of data in one place. And we may remove unimportant information from the dataset because we can do it. Why not? Yes, you may find more information about techniques to reuse your features, the amount of features in this link in the slide. So dimensional reduction may be divided into several categories. In the simplest way to divide it into groups using linear and non-linear criteria. In linear methods, we have principal component analysis, dependent component analysis, factor analysis, singular value decomposition, linear discriminant analysis, and others. In nonlinear, we have some nonlinear transformation of data. It's uniform manifold approximation, projection, isomap, and kernel principal component analysis. You see in this picture that in ordinary PCA, we find linear projections for the data and actually project our data set into some directions. But in nonlinear PCA, we have some kernel. This function actually, yes, and we project all our data set to this kernel and obtain a new data set with some new properties. Actually, the dimensional reduction technique can be also defined as it's a way of converting the higher dimensions dataset into less dimensions dataset, ensuring that it provides similar information. It's really important. These techniques are widely used in machine learning for obtaining a better fit predictive model while solving the classification and regression problems. So before classification, clusterization, and regression is good. It's really good to think about reduction of feature space. You may also use some empiric approaches in order to remove unimportant features for your analysis. You may using some rating to sort your features by impact to the results of classification, for example. I strongly recommend you to go to this link and read more about other techniques. As for principal component analysis, all mathematical explanation you will find in your lecture notes in PDF file, which uploaded to our classroom, and you may find really explanation using all mathematical methods. So I will explain you here the main idea, and we will try to calculate principal components in a simple example. So the main problem that's often the initial number P of features is quite large. For image visualization and recognition, simplifying the description and interpretation of datasets, compressing the size of dataset, and to make easier complex data analysis, we can significantly less than P measurements called principal components. So we go from our original features to principal components. The principal components are represented as a new set of extracted features. We will use Y for principal components. Each of them were obtained by some, it's really important, linear transformation of original features X, 1, 2, and P. So we have P features, yes, and we have P principal components. And U features are ordered according to the degree of dispersion in a population. The first feature had the greatest degree of dispersion, the highest variance actually. That means the greatest variance, and the second had less, and so on. So we just sort our principal components goes with the decreasing variance. The first one has the highest variance, second less, and so on. I have the first principal components had the highest variance, and we just we finding the direction where the variance of data set will be the highest. And the main idea is explained here. So in general, so we have 3 steps. Calculate the center of the data set. It's our 0 principal components. It will be actually some point. We need to standardize and normalize our data set in order to provide mean value is equal to 0, and it's better to provide standard deviation is also 1. Choose direction with the highest variance. So this direction with the highest variance will be our PC1. If data description is not full, you remember that we need to provide we need to do some transformation, but save information. Yes. If data description is not full and we need more directions, choose 1 or more directions, EC2, 3, and so on, perpendicular. It's important, actually, perpendicular to the first one, and continue this step several times. So number of times is equal to number of features. And you select PC2, which is perpendicular to your direction. Yes. And you may transform your original data space into a component space where you have PC1 and PC2 as X and Y axis. So you transform from 3D space into 2D. But actually, you will have the third principal components in your calculations, but you will not just use it in your analysis, in your future analysis. You just select the first and the second one. And you will have center here. So it's like a transformation. And actually, some visualization. So you have your data set where 1, 2, 3, it's number of observation. So you have objects in the row. Yes, and here feature 1, here we have features. So it's your original parameters. You plot it in a scatter, for example, you see that you have center, which is in 0, yes, normalized data, and you find direction with the highest variance. Variance like a range of your data set, and you see that in this direction, you have the highest variance, yes? Like, but actual variance, not the mean.
Sorry, I have a question. This is for real numbers. What about imaginary numbers? The same?
For imaginary numbers, you have real part and imaginary part, yes? So you may represent it using real and imaginary parts. It will be like features, more features, 2 times great, more feature than usual.
So we're going to have to split it into 2, into 2. Right?
Into 2 features, yes.
Mm-hmm.
I think that yes. Actually, we may work with imaginary numbers. It's okay, because we don't have mathematical limitations. We may calculate some of them, but we have some problem here. We have some limits for this linear transformation. I will read about limitation. It should be numerical, but I didn't see it should be real or could be complex. I will find it and write you what did I find. actually. Thank you for your question. And actually, one more animation. We just transform our original data space into a principal component data space. What about math here? Yes, the main idea is clear. Yes, we just transform it a little bit using linear transformation. What does it mean that we have linear transformation? It means that we have coefficients. Here you see L. Yes, it's really close to idea of linear regression. You remember that we have some coefficients and features, but in linear regression example, we had only one feature X, yes, and one response Y. But here it's a little bit more complicated, but not too much. So we have some limitation that all our coefficients should be sum of squares should be equal to 1, and all our principal components should be perpendicular one to another. As for covariance matrix, we need to covariance matrix represents variance of data set in multidimensional feature space. It's really the same idea which we have in ordinary variance in one-dimensional space, but corresponds to multidimensionals. Here we have our observations. Yes, and means here it's it's like this A. So we name the first principal component of the study general population for some observations such as normalized. It means that the length of this vector is equal to one linear combination of initial features x1, x, and so on. Yes, so it will be our first principal component, where we have, again, we have some vector of coefficients, yes, and some array of observations. And these coefficients should be selected in such a way which amongst all, which provides the greatest dispersion of the PC1. As for some information about covariance matrix, ordinary variance is calculated as follows. Yes, we have observations, we have mean value of the feature, calculate deviation from the mean value divided into number of observation minus 1. And when we are talking about covariance, so it's like how could we express variance of x using y? So it's like a dependencies, linear dependencies actually between two data sets. In multidimensional space, we are using this equation, and our covariance matrix consists of dispersions, ordinary dispersions here, and covariances out of the diagonal elements. It represents variation among the x's. Actually, it's close to the it's correlation coefficient actually. And the first value, the first principal component corresponds to the highest variance, but the ith principal component is also calculated in the same way. We have coefficients, but here we have some limitation. Yes, that all linear components should be independent. Yes, so correlation between principal components should be equal to 0. It's really, really important. And we have and the first principal component has the highest variance, the second less, and so on. And some information about how to calculate it. You may find this lecture in PDF file lectures. So our principal components are numbered in the decreasing order of the dispersions. And when we calculate dispersion of the principal components, there'll be like a mean value of this in square. And we obtain this parameter because x is independent. And second, the vector of coefficients for ith principal component, defining the transformation of a transition from initial features to y represents the so-called ith eigen vector of a covariance matrix that is, and these components. So could you just write to our chat, I'm familiar with the eigenvector and eigenvalue definition. So we need to calculate coefficients for our transformation, yes, in order to provide the highest variance for the first one and so on. It's not a problem actually. I show you the main idea of eigenvector and eigenvalue using this picture. So you may see this red arrow and blue arrow, and we transform this image, but using some transformation. You are very familiar. Hassan, you may also explain it to your classmates. It will be good. Hassan?
Okay, as far as I remember, the eigenvalues are the values, we use them in control systems actually. Just a second, I need to grab a piece of paper. Just to remember some stuff. So basically, I don't know how to explain it actually.
It's really hard to explain. Because you may understand
it's the determinant of A minus lambda in the uni matrix. So lambda are the eigenvalues of the matrix A, which makes the determinant of this A minus lambda lambda multiplied by I is equal to 0. So
yes.
Yeah,
exactly. So in just the core idea that we may transform our vector using eigenvalues and eigenvectors, but you don't change the direction of the, you see that blue arrow is the same for two cases. It means that this transformation, that this vector does not influence to your picture, which also some shape of vector. And the length is equal to 1, the scale of transformation of the length is equal to 1. This means that the eigenvalue is equal to 1. So you have some homework, yes, to read more about eigenvalues and eigenvectors, but I don't want, it's really only for your education. So we have some solution. We need to find solution of a system equation like the here. So in order to define some coefficients, yes, here. Read lectures, please, by your own. Try to understand what's going on here. And today we will calculate in some simplest way to find PCA. MATLAB can do it without any troubles. You just use function PCA, and that's all. And it returns coefficients and these principal components itself. Okay, we find coefficients for our principal components for our linear transformation. And if we have 10 features, we will obtain 10 principal components. But how to choose the correct number of components? And we want to be sure that we save important information. In principal component analysis, information is equal to variance. So we just use variance instead of information term. It can be two rules. We select number of principal components which describe 95% of the variance. And for principal components, we have some rule that sum of dispersion of principal components is equal to total dispersion of original data set. And we may plot these points. When we have only one principal component, it describes something about 67% of the dispersion, of the total dispersion. If you have two principal components, it describes a little bit more than 80%. And somewhere here, you see that you describe approximately 91% of the original dispersion. And you may say, okay, I will stop here. I will take 3 principal components. So maybe 4. Yes. And it will be about 95%. And also, you may select a required number of principal components. If you want to plot in 2D plot, you take only first and second principal component and plot it in your chart. That is stop rules. Principal components is not the best solution sometimes, and you need to understand limitation. When you have some classification task, you need to classify objects into 2 groups. In our example, it will be cats and dogs. And you transform your original data space in space of principal components. You calculate your principal component number 1, and you will see that you have some problem. After this transformation, you will find all your classes mixed. Yes, you see that cats and dogs mixed, and you could not separate these classes in 2 groups. But sometimes when your classes distribute in feature space better, for classification and principal component analysis before it, you may find this principal component, yes, project this objects into this direction, so find a linear combination, and you will see that your groups divide in 2 parts are really easy. So for the first case, your principal components really bad because you obtain worse results. In this case, you need to take second principal component. It will be somewhere here. So it's better to project your classes into PC2. But for the second example, principal components will help you to transform your problem from 2 dimensions into 1. Here we also see that we don't have some problems with transformation and everything is correct. Also, you may use principal component analysis for images. Again, here we have a link to find more information. There was a task to classify dresses which user like or not. So bad dresses and good dresses. Yes. It's picture. It's also 2D image, and of course it's better to reduce the size of this image to make performance faster and easier. You may select features or select principal components of this image and represent your image using these principal components. In this slide, you may see principal components of the dresses. Here also, it's like a main idea of the picture. And the first principal component, second, the fourth, and so on. You may just combine all of them layer by layer. You will obtain original picture. It's close to Fourier transform when you divide your signal into sum of several sinusoids. It's also the same idea. And also you may use principal components for images in order to split, in order to decrease the size of your data sets, and it means that you need less calculations in future when you work with this data, and you don't need to storage original data set. Okay. And in the end of this lecture, I want you to take some pencil and paper, because we will try to calculate the first principal component for a simple example of the data sets, just to understand the main, the core idea of this method. Please take some paper and pencil or pen. I will end an empty slide. One moment. Are you ready to write? Continue. Please write to our chat. You ready? Mm-hmm. Okay. Mm-hmm. So suppose we have two variables, two features, A1 and A2. It's our original data sets, and A1 will be equal to 4, 0, and A2 will be equal to 5, 1, 3. Firstly, we need to remove mean value from our original data set. So let's calculate mean value of A1 will be equal to what? Please calculate it by your own. Mean value of A1 and A2. You may say it orally or write to the chat. It's better to say it. Turn on your microphone.
It's 2 and 3.
2 and 3, exactly. So we may calculate x1 and x2, and let's will be, see that we have some chat. Sorry. X1 will be equal to A1 minus . And so here we have 0, 4, and minus 2. Yes. Here we have 2 minus 2 and 0. The next step, we want to find PC1. Direction with the highest variance. Yes, we know that PC1 is equal to some linear combination of x1 and x2. Let's suppose it will be a x1, a, it's not very good to use the same letter for two different variables, alpha plus x1 plus beta to x2. We know that alpha and beta numbers are numbers, and that the length of this vector is equal to 1. Yes, so it's our limitations. We need to provide PC1 has the variance of this PC1 should be maximum. And we optimize it for, we optimize it for our coefficients and beta, because x1 and x2 are constant. So we may vary only our coefficients. Okay, we have 0 mean value for x1 and x2. It means that the maximum variance of the PC1 will be when we have maximum maximum length of the PC1. So it will be maximum PC1 length. And let's take it in square because it will be better. So we need to maximize length of the vector PC1. Let's calculate PC1 here. For the first observation, we have x1, x2, 0, and 2. It means that we have PC1 is equal to B, 2B. Yes, for the second, we have 2 alpha minus 2 beta. And for the third observation, we have minus 2 alpha. Sorry, I need to take my chart. Continue. And we just calculate PC1 square like 2b square plus minus the second observation plus the second coefficient, actually, like here. So it will be like a variance, the highest variance of PC of this direction, with this alpha and beta coefficients. I forgot brackets here. It will be 4b squared. We open the brackets. Alpha squared minus 2 for beta plus 4b squared plus 4 alpha squared. We have beta square, alpha square squared will be equal to 8 beta squares plus 8 alpha squares and minus 8 alpha better. Yes. Do you remember the limitation that alpha squared plus b squared is equal to 1? So it will be equal to 8. Yes. 8 minus 8 multiplied by this 1. Let's divide our second part to 1. We may do it, why not? We need to modify our equation in such a way that now we have two variables here. Yes, but we know that alpha and beta depends from one from another, and we want to transform this equation in equation from one variable. After that, we just take I forgot the word, help me, extremum of the function when is equal to 0. What should be equal to 0 when we calculate the extremum value for the function?
Roots?
Not roots. I actually every time I forgot this word in English. The derivative. So we need to find the first derivative of this function when it will be equal to 0. It will be maximum or minimum of the function, because in point of the extremum, derivative of the function is equal to 0. So we will try to play with this expression and transform it to expression with one variable. So divide these some manipulations with the data set. We will have divide I have some problems with the words at the end of the lecture, sorry. We divide numerical and the numerical parts to lambda square and obtain something like this. And let's suppose that I will go to this part of the screen. Let's suppose that we have t is equal to beta divided by alpha. So let's use this new variable t. It means that we will have f from t, some function. Yes, it will be 8 minus 8t multiplied by 1 plus t squared. So we need to find the maximum of this function with t which maximize this function. So let's take the first derivative of this function, and it should be equal to 0. As you remember, we need to the numeric will be in square here, and first derivative of the numeric value, it will be 8 multiplied by this. After that, we take it without we take the derivative of the upper value. It will be 2t multiplied by numerator, like this. Yes, so it should be equal to 0. Denominator could not be equal to 0. It means if the function is equal to 0, it means that numerator is equal to 0. It will be 8 plus 8 to square plus 4. Oh, here should be not 2 but 8. Sorry for mistake. Should be equal to 16 t, and it will be minus actually. Minus t square 0 minus t square. And we have two solutions. Yes, t1, 2 will be plus minus 1. Yes. And there are 2 points of extremums. And we need to find which of two solutions corresponds to minimum value and which solution corresponds to maximum value. Could you just think a little bit about it? What solution -1 or +1 corresponds to maximum? When we are talking about maximum and minimum, we need to understand direction of the function. So if we have 2 points, it will be mean, it will be max. In the first part, our function increases, so the derivative of this part will be plus. The second part should be negative. So left, at the left, for the values less than maximum point, our derivative should be less than 0, or greater than 0. It means that the function grows, and it will be t. Yes, 0. And for the values that are greater than t1, our derivative should be less than 0. It means that after maximum, function goes down. So what do you think? What should we choose? -1 or +1?
It's supposed to be -1, right?
It will be -1. Yes, exactly. Let's select 0. When t is equal to 0, we will have a positive value of the derivative. It means that our function grows. Yes. Let's continue with our t. T is equal to -1. It means that our beta divided by alpha is equal to -1. Yes, and also we have the second limitation that sum of squares is equal to 1. Could you solve this system? Please find alpha and beta. You will also have two solutions. Yes, 1 divided by square root, yes.
Beta is √1/2.
Pardon?
Beta is √1/2.
1/2, why?
√1/2, square root of 1/2. Beta, square root of 1/2.
You mean this one?
No, square root of half. Yes.
That will be the same. So you may use square for the whole equation, or like this, it will be the same. You're right. You may use this or
If
this.
alpha is equal to beta, then I don't know. Are they not meant to be the same thing?
They are not the same. They are, have different sign.
Because from the equation, okay, -1. Oh my God, I used +1.
Ah, you mean that there should be equal. Okay.
Oh yeah, I used +1 instead of, sorry.
Okay. So you may choose one of these solutions, for example, this one, and construct your first principal component. It will be 1 divided by square root multiplied by x1 minus 1 divided by square root multiplied by x2. It will be your first principal component. You may take values from this data set, and you will obtain a vector. Actually, it will be 2 square root and minus. It will be your first principal component. It will be your points. So it's like an example of the idea. Yes, of course, calculations of coefficients a little bit more complicated when you have a lot of observations and you need to find the eigenvectors and values. But in MATLAB, we have PCA function, which allows us to use this method without any troubles. And you need only to understand what you're doing using this function and methods.
Wait, why do you have 3 values for PC1?
Because we have 3 objects in our data set. It's like a projection to the direction of which direction. When we are talking about vector of PCA, we have value of coefficients. Yes, so it's our alpha and beta. It's like a direction. When we need to project our data set into the direction, we will obtain 3 values because we have.
Okay, yes, 3 values. I understand now. I understand. X1 and X2. Okay, thank you.
Like a new feature, actually, not feature, but new column, new space. So in your lab work, you will work with principal component analysis using MATLAB, and I hope that it helps you to, this lecture helps you to understand what you're doing in your lab work a little bit more clear. So that's all that I want to say you about MATLAB or about principal component analysis. Questions? Okay. I stop record this